we are going to start a new chapter, that is Unit 7, Equilibrium. Equilibrium. What do you understand by the term equilibrium? Equilibrium is a state in which the properties means temperature, pressure and concentration of system do not undergo any further noticeable change with time is called equilibrium. So, we can say that at equilibrium, one of the properties, it can be either temperature, pressure or concentration, it does not change with time. Now, any equilibrium process involves two opposing processes. And equilibrium is attained when the rate of, when you say rate in chemistry, rate means speed. So, we do not use the word speed, instead we use rate. So, equilibrium is attained when the rate of two opposing processes become equal. And the mixture of reactants and products at equilibrium is called equilibrium mixture. Now, in general, we can represent an equilibrium as AA plus BB gives CC plus DD, where capital A, capital B, capital C and capital D. Capital A and B are the reactants, capital C and D are the products. Small a, small b, small c, small d, they are the stoichiometric coefficients. And the double arrow, this is the double arrow, it represents the reaction, that is, it is between the reactants and product. It shows that the reaction is taking place in both directions. Both direction means forward reaction taking place and backward reaction is also taking place, and these reactions are taking place simultaneously. Okay, so the double arrow indicates that both forward reaction as well as backward reaction takes place simultaneously. When forward reaction takes place, capital A and B are the reactants, capital C and D are the products. When backward reaction takes place, capital C and D are the reactants, capital A and B are the products. Now, there are two types of equilibrium which we have to study. So, one is physical equilibrium and the other is chemical equilibrium. In this video, we are going to study about physical equilibrium. So, let us discuss in detail about physical equilibrium. Physical equilibrium. If the opposing process involve only physical changes, it is called physical equilibrium. Now, we have 5 types of physical equilibrium to study. The first type is solid liquid equilibrium. So, the first type of physical equilibrium is solid liquid equilibrium. Now, example for the solid liquid equilibrium is melting of ice. Now, to study this, we take ice along with water at 273 Kelvin. 273 Kelvin means 0 degree Celsius and normal atmospheric pressure. And this ice along with water is taken in a thermo flask, so that no heat can leave or enter the system, which means the mass of ice and water remains constant. Now, here you can see in the beginning ice will melt and it changes into liquid water. After some time, the liquid water will freeze and go back into solid ice. So, here the two opposing processes are melting of ice and freezing of water. Okay, and we can say that at equilibrium, the rate of, finally what happens, an equilibrium is reached, and at equilibrium we can say that at equilibrium rate of melting of ice is equal to rate of freezing of water. Also, both the process at equilibrium, both the process, that is melting of ice and freezing of water, takes place simultaneously. So, both process occurs simultaneously. And also we can say that we can represent that equilibrium between the solid ice and liquid water as H2O solid. This is our ice in equilibrium with H2O liquids. Also, we can give a definition for melting point or freezing point. Melting point or freezing point can be defined as the temperature at which solid and liquid form of pure substance exist in equilibrium. It is called the normal freezing point or melting point of that substance. So, this is the first type of physical equilibrium, that is solid liquid equilibrium, and we know at equilibrium the rate of melting of ice is equal to rate of freezing of water. Also, both processes occur simultaneously, and we can represent that equilibrium as H2O solid in equilibrium with H2O liquid. And here the physical quantity that remains constant is melting point or freezing point, which is the temperature at which the solid and liquid form of a substance exists in equilibrium. Now, the second type of physical equilibrium is liquid vapor equilibrium. So, second type is liquid vapor equilibrium. Now, liquid vapor equilibrium, the example is evaporation of water. Evaporation of water. Now, to study this liquid vapor equilibrium, let us take water in a closed container and a manometer. Manometer is an instrument used to measure the pressure, the vapor pressure. Manometer is attached to this closed vessel, and this manometer contains mercury inside it. Now, we have taken the liquid water in the closed container. You can see after some time, it is a closed container. So, after some time the liquid water evaporates and changes into vapor state. So, when it changes into vapor state, you can observe that the level of mercury in the manometer increases. Now, after some time you can see the level of mercury in the manometer decreases, because the vapor, some of the molecules from vapor has condensed. Condensed means cooled and go back into liquid state. So, what happened? The vapor, that manometer reading decreases, and finally what happens? An equilibrium is established. So, at equilibrium we can say the rate of evaporation is equal to rate of condensation, and at this point, that is at equilibrium, we can see the mercury reading in manometer remains constant. And you know that increase and decrease in the mercury reading is due to the formation of vapor pressure inside the closed container. Now, what do you mean by the term vapor pressure? Vapor pressure is the pressure exerted by vapor in equilibrium with liquid at a particular temperature. So, when you see the vapor pressure remaining constant, we can say that that system has attained equilibrium. So, in liquid vapor equilibrium, we can say that at equilibrium we can say the rate of evaporation is equal to rate of condensation, and both the process occurs simultaneously at equilibrium. That is, at equilibrium, the number of water molecules going into vapor state and the number of particles coming back to liquid state remains constant. And also we can see, or we can give a definition for vapor pressure here. Vapor pressure is the pressure exerted by vapor in equilibrium with liquid at a given temperature. And we can also say that this vapor pressure, or we can represent the equilibrium as, the equilibrium is represented as water in liquid state in equilibrium with water in vapor state. This is how we represent the liquid vapor equilibrium. And we know that as temperature increases, vapor pressure increases, means more and more substance can go into vapor state, means the substance is more volatile, and the liquid which has higher vapor pressure has lower boiling point. So, that is the relation between vapor pressure and boiling point. Now, in this case, the physical quantity that remain constant is our vapor pressure. Okay. Now, next is the third type of physical equilibrium, which is solid vapor equilibrium. So, the third type, number 3, is solid vapor equilibrium. Now, what do you observe in solid vapor equilibrium? And an example for this solid vapor equilibrium is the sublimation of iodine. You know that the process of conversion of solid directly into vapor state is called sublimation. So, let us discuss this taking iodine as example. Iodine. Now, you take iodine in a closed vessel. After some time, you can see that vessel gets filled with violet vapors of iodine, and in the beginning the intensity of color is very high. Now, after some time, you can see what happened. This iodine vapors will condense and go back into solid iodine, and this is observed as decrease in intensity of color. Finally, we can see the color remains constant, which means that the system has attained equilibrium. So, we can say at equilibrium, rate of sublimation is equal to rate of condensation, and both the process, that is sublimation and condensation, takes place simultaneously, and we can represent that equilibrium as I2 solid, iodine in solid state in equilibrium with iodine in vapor state. Now, there are other examples for the solid vapor equilibrium. Other example is camphor. Camphor in solid state is in equilibrium with camphor in vapor state. Now, one more example is given, that is ammonium chloride. Ammonium chloride is a solid which can easily sublime, is in equilibrium with ammonium chloride in vapor state. So, these are the different examples. Okay. So, these are the 3 types. Now, the 4th type of physical equilibrium is solid solution equilibrium. So, the 4th type is solid solution equilibrium. Solid solution equilibrium. An example for this is dissolution of sugar in water is an example for solid solution equilibrium. So, example is dissolution of sugar in water. Now, let us discuss this. First, you take sugar, solid sugar in a vessel, add water to it, it becomes a solution. Now, you keep on stirring the solution, we can see that the sugar dissolves. Now keep on adding more and more sugar, sugar will dissolve, and finally you can see a point where the sugar does not dissolve in water. Now you heat that solution. What happens on heating the solution? That sugar which was left undissolved will dissolve in water. Now you keep on adding more and more sugar to this hot solution, more and more sugar particles will dissolve, and finally again a stage is reached when no more sugar particles can dissolve, and we call that stage as unsaturated solution, or we call that solution as unsaturated solution. So what do you mean by an unsaturated solution? A solution in which no more solute can be dissolved is called an unsaturated solution. Now you cool that unsaturated solution, you call it a saturated solution. Okay, not unsaturated, saturated solution, because maximum amount of sugar is dissolved. So unsaturated solution means a solution in which more and more solute particles can be dissolved. Now we have saturated solution. Saturated solution means solution in which no more solute particles can be dissolved. Now in saturated solution, you keep that saturated solution to cool. What do you observe? You can see that from that solution, some of the sugar molecules will crystallize out on cooling, and they come back to our solid sugar crystals. And finally, you can see an equilibrium is established between the sugar particles and the sugar particles in solid state and the sugar particles present in solution, and you get this equilibrium in a saturated solution. So in a saturated solution, equilibrium exists between the solute molecules, that is sugar molecules in solid state, and the sugar molecules in solution, and we can represent it as sugar solution in equilibrium with sugar solid, and also at equilibrium we can say rate of dissolution of sugar is equal to rate of crystallization of sugar, and at equilibrium both the process, that is dissolution process and crystallization process, takes place simultaneously. So this equilibrium is established only in a saturated solution. Saturated solution means a solution in which no more solute can be dissolved. Okay. And unsaturated solution means more and more solute can be dissolved, but equilibrium can be established only in saturated solution. So this is our fourth type of physical equilibrium, that is solid solution equilibrium. Now the last type of equilibrium is number 5. Last type is gas solution equilibrium. Now example for this is dissolution of gas in a liquid under pressure. Dissolution of gas in liquid under pressure. Now example for this is you can see soda water which is sealed and it is kept closed under high pressure. When inside that bottle, soda bottle, you can see that carbon dioxide gas, maximum amount of carbon dioxide gas is dissolved, and that bottle is at high pressure. Now inside the bottle we can say that carbon dioxide gas is in equilibrium with that carbon dioxide solution. Solution means the carbon dioxide dissolved in water. Okay. Now what happens when you open the bottle? You can see the soda water fizzes out. Now what is the reason for that? Now that equilibrium is disturbed. So this soda water, it wants to attain new equilibrium. So by reducing its pressure also decreases when you open the soda bottle. So to attain that new equilibrium, that soda water fizzes out, and we can see that equilibrium is established. Again, new equilibrium is established between carbon dioxide gas and carbon dioxide in solution. So we can say that as pressure increases, solubility of gas in liquid increases. Okay. Now when you open the bottle, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition needed for the lower pressure. Now also there is a law called Henry's law. Henry's law, that equilibrium is governed by a law called Henry's law for gaseous system, and the law states that the mass of a gas dissolved in a given mass of solvent at any temperature is proportional to the pressure of the gas above the solvent, which means mass directly proportional to pressure, or mass is equal to K into P, where K is a constant called Henry's law constant. K is called Henry's law constant. Okay. So these are the 5 types of physical equilibrium. Now to sum up, let's see once again. For solid, the first type was solid liquid equilibrium. For solid liquid equilibrium, the melting point or freezing point is the temperature which remain constant, and the physical quantity that remain constant there is temperature. Second is liquid vapor equilibrium. The vapor pressure is constant at a given temperature. Now for the third one was solid vapor, which is sublimation, and there we had the color that remain constant. Now the next is for dissolution of solid in liquid, the solubility of solid in solution is constant. And the last is for dissolution of gases in liquid, the mass of gas dissolved is constant at constant pressure. So these are the 5 types of physical equilibrium. Now let us see the general characteristics of equilibria involving physical process. So let us discuss the general characteristics of physical equilibrium. General characteristics of physical equilibrium. The first one is equilibrium is possible only in a closed system at a given temperature. Second, both the opposing processes occur at the same rate and there is dynamic but stable condition. 3. All measurable properties of a system remain constant. When equilibrium is attained for a physical process, it is characterized by constant value of one of its parameters at a given temperature. And the last one, the magnitude of such quantities at any stage indicates the extent to which the reaction has proceeded before reaching equilibrium. So these are the 5 characteristics of a physical equilibrium. So with this we complete the physical equilibrium. Thank you.